Hello, I am Alex and I will introduce to you Data-Centric Python, a subset of Python that retains the language's productivity but is also portable and highly performant. So, first of all, why Python? Because it is the language of choice of scientists. And why is that? We can summarize this to its vast and productive software ecosystem. Here we have to start with NumPy and SciPy, which implement all the basic math and integrate with libraries such as BLAS and LAPACK, which accelerate the runtime execution. Python has modules for data and network analytics, symbolic computations, visualizations, and many more productivity tools. And all this productivity has already led to the development of very large scientific applications, for example, in molecular dynamics, weather and climate, material science, and deep learning. Now, these applications are not just scientific applications. They're high-performance computing applications. So the question changes to, is Python an HPC language? To answer this, we must investigate the portability of Python. Can we run it on different state-of-the-art hardware architectures? And if yes, can we do so while achieving high performance? As a first attempt to answer these questions, let's have a look at productivity and performance. What is the relationship between those two? Do they go together, or is there some kind of trade-off? To provide an intuitive example, I present to you on the left reference C code that implements the naive algorithm for the general matrix-matrix product. On the right, you can see the same operation written in Python using the conveniences provided by the NumPy module. We can already see that the Python code is much shorter, just a single line. This means that it's much easier to read, write, and understand its functionality. We can attribute this to the explicit matrix-matrix product operator, the @ symbol, but also to the implicit operations among arrays and scalar values. However, what does this mean for performance? To find out, we execute this code on an Intel Xeon CPU machine with 32 cores and compare the execution runtime of the reference CPython interpreter with frameworks that accelerate Python. Two of those frameworks are NumPy and Python, and they execute the code about 40% faster than the CPython interpreter. This is definitely a large improvement, but on the other hand, it shows that the CPython interpreter is not, in this particular case, as slow as someone might expect. Another Python accelerating framework is SciPy, which executes NumPy operations directly on NVIDIA GPUs. SciPy executes this operation on a V100 GPU about 17 times faster than the CPython interpreter or the Xeon CPU. This is a healthy speedup and perhaps something we can expect due to the different compute capabilities of these two chips. What is interesting to do, though, is to compare the Python executions with those of the reference C code compiled with two standard and commonly used compilers, the GNU C compiler, or GCC, and the Intel compiler, ICC. Here we see significant performance differences. GCC in particular is quite a bit slower for a number of reasons. First, it doesn't autoparallelize. So we are looking at a single-threaded execution against executions that may take advantage of all 32 cores on the machine. Furthermore, the reference C code consists of 3 nested loops, which is hard to optimize. This code may run fast only if we tile these loops repeatedly, one for each level of the memory hierarchy, in order to take advantage of locality. GCC cannot do this automatically, at least in this example, and therefore has a slow execution. On the other hand, the Intel compiler pattern matches BLAS operations, for example GEM, and substitutes them with calls to the optimized MKL library. However, this doesn't always work that well, as we see here. There is significant improvement compared to GCC, but ICC is still not as fast as Python. To confirm that this is not a fluke, we have a couple more examples. These are kernels that perform 2 and 3 matrix multiplications respectively. The results are very similar. Now, just to get this out of the way, Someone could claim that the comparison is unfair. We are, after all, comparing a naive implementation of matrix multiplication in C with an explicit matrix multiplication operation in Python that can abstract away calls to MKL, OpenBLAS, QBLAS, or any other optimized BLAS library. This is what NumPy does. And perhaps a more apples-to-apples comparison will be against C code that also calls BLAS or MKL. However, the main point that I would like to make here is that Python and NumPy do this abstraction for the user automatically. So I can be some random person that has no idea about what BLAS and GEM is, but as long as I can write this very simple code, I can get very high performance. In fact, very close to the peak performance of the machine. However, let's have a look at another piece of code. So, can we always get the same results across all kinds of programs? Well, spoiler, no. Here we have a second example, a finite time difference domain stencil. Again, on the left is the reference C code, while on the right is the Python code using implicit array operations with NumPy. The Python code is still shorter than the C code, but what about the performance? So NumPy and CuPy are 4 and 40 times faster than the C Python interpreter respectively. And what about the C compilers? Well, GCC with always a single threaded execution is almost as fast as NumPy on a 30-core CPU, while ICC is the fastest on the CPU, almost as fast as CuPy on the NVIDIA V100 GPU. And it's also only 10 to 11 times faster than GCC. And perhaps we can see here that there is more performance left on the table to exploit. Now, again, to make sure that this is not just a fluke, we make the same test with a couple more similar stencil codes, Jacobi QD and Hit3D, and we see the same picture. So, what is exactly the issue with these stencil codes and the C Python interpreter? So, let's focus on a specific line in the Python code and the equivalent loop nest that implements it in C. Now, the C Python interpreter executes the operations from right to left. Therefore, it will first subtract the two slices of the HZ matrix and store the output in a temporary array. Afterwards, it will multiply this intermediate result and store it in a second temporary array. And finally, it will execute the augmented assignment. Now, on the other hand, the reference C code has no such temporary arrays slowing down the execution. The operations are fused together. So, why cannot the C Python interpreter do the same? Because Python does not analyze the data movement, and in this case, it cannot infer the capability to fuse and take advantage of locality. This is exactly one of Python's performance disadvantages that we want to fix. So, how are we going to do this? We start with Python and its features. So, we have features like dynamic typing and dynamic attributes that are increasing productivity, while others, well, for example, the NumPy module, are more tailored for performance. Now, we study this feature and check which of those inhibit program analyzability. Like, for example, when we use dynamic typing, we can write code such as the one that you can see on the screen, where the type of values can only be inferred during runtime. Or with dynamic attributes, we can define a class, and then we can essentially inject new attributes to object of this class during runtime. So such codes are not statically analyzable and make performance engineering hard. Therefore, we want to constrain such features. So, for example, maybe we want to ask the user to provide type annotations, or maybe we want to disallow dynamic attributes completely. And this allows to analyze the data movement. Now, since we are interested in high performance computing, we also want to add to Python some extra features that are tailored for this. So, for example, we want to retain the just-in-time nature of the CPython interpreter, but we also want to enable ahead-of-time compilation, because most people do not want to spend their precious node hours in a supercomputer compiling programs. They want to run the applications and get results. Now, since we are interested in parallel computations, we also introduce a parallel loop construct. So Python does not have by default one, and we resolve this issue by adding a parallel loop iterator that we call a map. So finally, we add an interface that allows us to describe distribution and communication of data, and more on that later. Now that we have roughly defined what data-centric Python is, let's have a look at how we can integrate it in our workflow, as this is implemented by Dace, the data-centric framework. We start with Python NumPy code constrained to data-centric Python. We parse this Python program and we automatically generate a data-centric intermediate representation, which we call SDFG. This is short for Stateful Data Flow Multigraphs. Now, in this representation, we apply data-centric and device-specific transformations in order to optimize it. These transformations can be applied manually by the user utilizing a programmatic API, but also by using graphical tools. However, we also have auto-optimizations heuristics that we will discuss shortly. In the last step, we generate device-specific optimized code utilizing backends that exist in Dace for different hardware architectures. Now, let's focus on the first half of this workflow and how we map data-centric Python code to SDFGs. So I will use as an example a Python function. So first we need to tell the framework to parse this function. We achieve this by adding before the function definition the Dace program decorator. If you are not familiar with Python decorators, it is enough for this talk to think of them as some kind of annotation. So this annotation says that the function that follows is a data-centric Python program. Now, in the data-centric model, we separate containers, or data if you prefer, from computation. So these data containers are represented by ovals that we call access nodes. Now, the fine-grained computation is represented by polygons called tasklets. Now, the access nodes and the tasklets are connected by edges, representing the data flow explicitly. These edges have annotations called memlets, which show the exact subset of data that is being accessed. However, this is not always enough. Whenever the order of the program execution is not implied by the data flow, we insert explicit control flow. To that end, we encapsulate pure data flow in blue rectangles that we call states, and then we connect these states with edges annotated with the required control flow. Now, in the example program, we can see that we can represent for loops, if conditions, break, and return statements. And you can see on the right how these elements can be represented in SDFG. Now, a last important concept of the data-centric model that I would like to talk to you about is coarsening. So this is the capability to abstract away unneeded details or to hide them temporarily to allow seeing the big picture, only to focus on them later when needed. Now, the code, the example Python function has two cases of coarsening. So first, we have a function call that perhaps can be another Python program and can be represented by a nested SDFG, or if it's code in another language, for example C++, we can represent it with something that we call a code node. A second coarsening case is the map that was mentioned earlier and is a set of independently parallel iterations. So a map is represented in the SDFG as a scope opened and closed by two trapezoids, the map entry and the map exit nodes. Now that we introduced the SDFG intermediate representation, let's see how we can optimize it. To that end, let's go back to the stencil example and focus again in that particular line that showcased the performance inefficiencies of the CPython interpreter. Starting again from the right, we first have the subtraction of the two slices of the HZ matrix and is represented in the SDFG by a map, since it's an operation that can be executed in parallel. And the output is written into the transient temp1. The multiplication by 1/2 applies on temp1 and produces temp2. Finally, the augmented assignment produces a third map. Now, we already saw from the reference C code that we can fuse these maps together. The SDFG representation allows us to analyze the data movement and infer automatically the safety of fusion. We call this transformation subgraph fusion. It searches in a greedy manner for all the maps in a data flow state that are directly connected with each other and exist in the same iteration space and fuses them together, resulting in an SDFG that you can see on the right. Now, if we automatically generate C++ code for this optimized subgraph, we can see that it looks very similar to the reference C code. There is a set of two nested loops computing and writing directly to the EX matrix without storing any intermediate results in transient arrays. However, please note that we also get automatically OpenNP annotation, allow us to take advantage of multi-core CPUs. Now, apart from subgraph fusion, we have a lot more transformations. I will present to you a few. Here is a subgraph where we have direct copies among multiple data going through temp. Let's assume that the data temp is only used here and nowhere else in this program. In this case, we can automatically detect that there is redundant and wasteful copying of data. With the redundant array transformation, we can eliminate this inefficiency. Next, we have a for loop as it is represented in SDFG. If we check the memlets, we can see that in each iteration of the for loop, a unique index of the data is accessed. Therefore, the iterations are independent of each other, and we can be safely executed in parallel. Now we have a transformation, we call this loop to map, and as the name says, converts a for loop to a map, allowing multi-threaded execution. Let me show you here another map with a new SDFG element. It is this dotted edge that connects the map to the output data alpha, which is a scalar value. A dotted edge in SDFG represents write conflict. The reason that we have write conflict here is that multiple threads write to the same memory location. This means that we must use atomics to ensure preservation of program semantics. However, atomic operations can cause cache invalidation and in general be slow. Now we have a transformation that tiles the map and the write conflict. So here what happens is that the outer map is now having a parallel schedule and is executed by multiple threads, while the inner map is executed sequentially and individually by each thread. The tiling automatically introduces a scalar variable temp that is private to each thread and allows partial accumulation without the use of atomics. So writing from the private variables to the global variable alpha still requires atomics, but all the other writes in the write subgraph do not. Therefore, the execution can be much faster. I have one more important transformation to show you, and I will go back to the gem example. So this is how matrix multiplication between two matrices is represented in SDFG. The operation itself is represented what we call a library node for this specific operation. So this is an abstract representation that we have to make concrete before we generate code for a specific architecture. So we call this library node expansion or specialization, but this is a very similar concept to the lowering of MLIR. So what we do is we lower or specialize this abstract representation for one that is optimized for the architecture that we are targeting. Like for example, for the GPU, we may want to expand this to an MKL or an OpenBLAS call. For NVIDIA GPU, we use cuBLAS, and for FPGA, we have systolic array implementations. Now, Dace has a lot more transformations. We put them all together, we make a recipe, and we end up with automatic optimization heuristics that we can apply to any data-centric program with a click of a button. Now, by click of a button, I mean that we set a parameter in this Dace program decorator that we saw earlier, bigger button not included, sorry. Now, let's go back to the program samples that we saw earlier. And let's see what these automatic heuristics can do for our Python codes. So now we add here Dace that executes the Python NumPy codes, and it is actually as fast or even faster than all the other Python frameworks and the C compilers. Now, of course, 6 codes are a very small sample. This is why we will use a much larger pool of programs to make performance comparison. This is NumPyBench or NPBench if you prefer, which consists of more than 50 kernels and micro benchmarks from a wide range of scientific applications written in Python. Now, going over every single code will take too long, so I will just give you the summary. Now, on CPU, Dace is more than 10 times faster than the reference CPython interpreter, but it's also about 2 times faster than NumPy and almost 4 times as fast as Python. And this is always with automatic optimization heuristics. There is no manual tuning or optimization. Furthermore, for the subset of samples where there is equivalent C code, we compare against GCC and ICC. And we find the Dace is 9.3 and 2.3 times faster respectively. Now on the GPU, Dace is 3.75 times faster than CuPy. Now, as was mentioned before, Dace can support more architectures than just CPUs and GPUs. For example, FPGAs, and it can do so with both Intel OpenCL and Xilinx HLS backends. Now, at least at the time that this work was submitted, we couldn't find any other comparable framework that could automatically parse Python and NumPy codes and run them on the FPGA. Therefore, we have no performance comparison, but the takeaway is that Dace can do so automatically. Now, let's move on. We are in HPC, and of course, we usually target distributed memory machines. So Dace has the capability to transform SDFGs to execute in such machines, and in many cases automatically. Now, for example, if we have some array scalar operation, like the one that we see here on the left, we can distribute it with a transformation in the following manner. So we start with the global view of data. So this is the, let's say, alpha and beta arrays here. And what we want to do is we want to move to the local view of the data. So the local A and local B that exist in the local memory of each node in the cluster that are going to be used to perform the local computation. So we bridge these two views by inserting between them collectives that are represented by suitable library nodes, and that we can later lower them to NPI implementations. Now, another way with which Dace can automatically distribute computations is library specializations. So we already saw how a library node, for example, matrix multiplication, can be lowered to optimized implementations for different hardware architectures. To support distributed memory machines, we simply need to add another specialization. So, for example, we can now have a subgraph that utilizes NPI collectives and a scale-up PBLAS gem call. And let's right away now an actual example. So there is the GESUMMV kernel. This kernel consists of matrix vector multiplications, and we perform quick scaling experiments on the Piz Daint supercomputer up to about 1300 CPUs. Now on the left we have the runtime execution, and on the right figure we have the parallel efficiency. And Dace achieves at scale almost 70% parallel efficiency. Now, to validate how good this result is, we make a comparison against two other frameworks that can execute Python workloads on distributed machines. So this is Dask in blue and Ligate in green. And we can see that Dace is both faster than them, but also achieves a higher parallel efficiency. Now, let's say that we have some larger application where the distribution it's not so easy to find. And perhaps the automatic distributions that we saw before are not good enough. And maybe the user wants to get direct control over the communication and the distribution scheme. So Dace allows this, and let me show you how. So here we have a code snippet from another stencil kernel. So this is Jacobi 1D. So the user can adapt the code and describe the desired distributed schemes using an interface that is very similar to NPI. So for example, I show you here a very common pattern. We use I-sends, I-receives, and wait all to get all the data that are needed for the computation, and then we actually perform the computation. And let's see how actually this code performs, or to be more specific, the 2D version of it, Jacobi 2D. We perform again weak scaling experiments on the Piz Daint supercomputer, again up to 1300 CPUs. And again, we have on the left the runtime and on the right the parallel efficiency. In this example, Dace achieves almost 80% parallel efficiency at scale. And if we compare with Dask and Ligate, Dace is again faster and more efficient. Now, in the paper, you can find more distributed results, both with automatic distributions, but also with user-driven communication schemes. Let me give you again the summary. So Dace has better parallel efficiency by about 2.5 and 1.7 times compared to Dask and Ligate, respectively. To conclude, I presented to you data-centric Python, a subset of Python that retains the language productivity, but is also portable. We can run this on CPUs, GPUs, FPGAs, and also distributed memory machines. And data-centric Python is also highly performant. Now, the data-centric framework is open source and is actively developed on GitHub. Try it today.